What does it feel like to want something that the laws of nature have made permanently, mathematically, cosmically impossible? Not difficult, not expensive, not merely dangerous. Impossible. We are a species that has split the atom, mapped the human genome, and placed footprints on another world. And yet there is a destination, the nearest one, the very next star along that we cannot reach. Not today, not in a century, possibly not ever. And the reason isn't a lack of courage, or funding, or imagination. The reason is written into the fabric of space and time itself. So what do we do with a longing the universe will not permit us to fulfill? I have been thinking about that question for a long time, and the more I sit with it, the more I believe it is one of the most important questions our species has ever faced, not because of what the answer tells us about space, but because of what it tells us about ourselves, about the nature of hope, about the difference between ambition and wisdom, about what it means to understand something completely and to love it anyway, even knowing you can never touch it. So today, I want to take you on a journey. Not a journey through space we will discover, together, why that particular journey is beyond us, but a journey through the truth of our situation, through the physics, the biology, the mathematics, and finally, the philosophy of what it means to be a small, warm, astonishing species stranded on one pale world, staring across a void it cannot cross. Stay with me, because by the end of this, I promise you, you will feel something shift. Not despair. Something rarer and more durable than that. Something that I think is closer to wonder. Let us begin with the distance. Because the first thing we must do, before anything else, is feel the size of what we are talking about. Not understand it, in the way you understand a fact you've read and filed away. Feel it. Let it settle into you, like a stone dropped into still water. You know the moon. Most of us have looked up at it on a clear night and felt that particular pull, that ancient, wordless recognition. The moon sits approximately 384,000 kilometers away from us. That is far enough to feel genuinely remote. And yet, and here is the thing that matters, the Apollo astronauts reached it in about 3 days. 3 days. That is a long weekend. That is the time it takes to drive across a large country. In cosmic terms, the moon is practically in our garden. Now consider the sun. 150 million kilometers away. Light, the fastest thing in the universe, the thing that nothing can outrun, takes 8 minutes and 20 seconds to cross that distance. If the sun were to simply vanish, to disappear without warning at this very moment, you would not know for over 8 minutes. You would sit in what felt like a perfectly ordinary afternoon, and then the light would fail. That is how large that gap is. And yet, we have sent probes to the sun. We have studied it, measured it, photographed its surface in extraordinary detail. The Parker Solar Probe, humanity's fastest creation, can reach the sun's neighborhood in a matter of months. But these distances, the moon, the sun, are nothing. They are crumbs on the table. They are a single step in a walk that has barely begun. Proxima Centauri, our nearest stellar neighbor, sits roughly 40 trillion kilometers away. 40 trillion. I know your mind skipped over that number. Mine wants to as well. So let me try to make it real for you in a different way. Let us shrink everything down. Imagine you are holding the Earth in the palm of your hand, compressed, impossibly, to the size of a small glass marble. On that same scale, the sun would be a ball about 30 meters away from you. 30 meters. You could walk there in half a minute. And Proxima Centauri, our nearest neighbor, the closest star, the one we talk about when we dream of going somewhere else, would be 8,000 kilometers away from that marble in your hand. 8,000 kilometers. That is roughly the distance from Lagos to Tokyo. From Cape Town to Alaska. From one side of the planet to the other. Your marble Earth. Your 30-meter sun. And then 8,000 kilometers of absolutely nothing before you reach the very next star. That is the canyon we are standing at the edge of. That is what we are looking across when we talk about interstellar travel. Now, how fast can we actually go? The fastest object humanity has ever built, the Parker Solar Probe, moves at its peak velocity of around 700,000 kilometers per hour. That is fast enough to fly from London to Sydney in under 2 minutes. When you first hear that, Something in you wants to feel reassured. Surely, at that speed, we could get somewhere. Surely that is fast enough to matter. It is not. At that speed, the absolute fastest we have ever achieved, the pinnacle of everything our civilization has ever built and launched it, would take over 6,000 years to reach Proxima Centauri. 6,000 years. 6,000 years ago, human beings were just inventing writing. The pyramids had not yet been imagined, let alone built. If the ancient Sumerians, on the very morning they pressed the first mark into clay and created the written word, had launched a spacecraft at Parker Solar Probe velocities, it would still be traveling now. It would not arrive for another 4,000 years. That is not an engineering problem. That is a confrontation with the geometry of the universe itself. And there is something I should add, because the comparison is perhaps even more sobering than it appears. The Parker Solar Probe only reaches those extraordinary speeds because it is falling toward the sun, borrowing energy from the star's enormous gravitational pull. A spacecraft heading outward, away from the sun, toward another star, would be fighting that gravity the entire way. It would be slower. Much, much slower. Voyager 1, which has been traveling since 1977 and has now officially crossed the boundary of our solar system, becoming the most distant human-made object in history, moves at around 61,000 kilometers per hour. At that pace, the journey to Proxima Centauri would take over 73,000 years. 73,000. And Voyager 1 is not even pointed in the right direction. We sent our furthest emissary into the dark, and it cannot reach the very next address. So we need to go faster. That much is obvious. The question is how? And this is where the physics begins to turn against us in ways that are not intuitive, not obvious, and not, I am afraid, solvable with more money or more willpower. You might think, bigger rocket, more fuel, accelerate harder for longer, push the spacecraft faster and faster until the journey becomes feasible. On paper, this sounds reasonable. In reality, it leads directly into one of the most merciless equations in all of engineering. It is called the Tsiolkovsky rocket equation, and it does not negotiate. Here is what it tells us, in plain language. The faster you want to go, the more fuel you need. But fuel has mass, and that mass needs to be accelerated along with everything else, which means you need more fuel to accelerate the fuel. But that additional fuel also has mass, which requires more fuel. The cycle does not stabilize. It spirals exponentially. The fuel requirement grows faster than the speed gain, and it does so without limit. To accelerate even a modest spacecraft, something small, something stripped down to the bare essentials to 10% of the speed of light using conventional chemical rockets, you would need more fuel than currently exists on Earth. Not more than we have stored. More than exists on the entire planet. We are not talking about building a bigger fuel tank. We are talking about a requirement so enormous it shatters the concept of rocketry entirely. This is why no amount of funding, no act of political will, no engineering genius working within the framework of chemical propulsion will ever solve interstellar travel. The physics will not permit it. The rocket equation is a wall, and chemical propulsion runs straight into it at speed. But there are other kinds of engines, and here I want to be fair, because human ingenuity is a remarkable thing, and it has not simply accepted this wall without looking for a door. Ion thrusters work differently. Rather than burning fuel in a violent, explosive reaction, they ionize a gas, often xenon, and use electric fields to accelerate the charged particles out of the back of the spacecraft. The thrust this produces is extraordinarily small. We are talking about a force roughly equivalent to the weight of a single sheet of paper. It is almost nothing. And yet, and this is the elegance of it, it can run continuously. For months, for years, while a chemical rocket burns brilliantly and briefly, an ion thruster whispers its acceleration across time, building speed slowly and patiently. NASA's Dawn spacecraft proved the concept works. It orbited 2 separate bodies in the asteroid belt using ion propulsion, something that would have been impossible with conventional rockets. Then there is nuclear thermal propulsion. A nuclear reactor heats hydrogen to extraordinary temperatures, causing it to expand and blast through a nozzle, producing thrust, It is roughly twice as efficient as chemical rockets. NASA has invested seriously in this technology, and there are genuine reasons to believe it could be built. And then there are the wilder proposals. Nuclear pulse propulsion, an idea explored with genuine seriousness in the 1960s under the name Project Orion, envisions a spacecraft that rides the shock waves of nuclear explosions, detonated behind it. A series of small atomic bombs, one after another, each detonation pushing the craft faster. It sounds like science fiction of the most colorful kind, but the physics, when examined carefully, is not entirely unreasonable. Theorists believe such a system could reach a few % of the speed of light. And here is where I must pause, because even the most ambitious, most technically radical of these proposals, the ones that exist, for now, only on paper and in the minds of extraordinarily clever people, gets us to somewhere between 5 and 10% of the speed of light. At 5%, the journey to Proxima Centauri takes approximately 85 years. At 10%, around 43 years. Better than 6,000 years certainly, but still an entire human lifetime. Still a journey that no one who boards the ship will survive to complete. And none of these systems, in any form capable of carrying human beings, currently exist. We are speaking of concepts, of blueprints, of theoretical frameworks awaiting funding, political will, and decades of engineering work that has not yet begun. But let us imagine, for a moment, that we solved it. Let us grant ourselves the luxury of assuming that some future civilization, perhaps our grandchildren, perhaps their grandchildren, manages to build a ship capable of traveling at a significant fraction of light speed. A ship that can sustain a crew across decades of deep space travel. Let us say we solved propulsion entirely. What then? Then we encounter the hardest wall in all of physics. And this one has no door. Einstein's theory of special relativity, now confirmed to extraordinary precision by over a century of experiments, tells us something that sounds simple but carries enormous weight. Nothing with mass can travel at the speed of light. Not approximately the speed of light. Not 99% of it. Not with some clever trick or shortcut or future technology we haven't imagined yet. The reason is absolute. As an object with mass accelerates toward light speed, the energy required to push it faster does not merely increase. It approaches infinity. Not a very large number. Infinity. You could capture the entire energy output of our sun, every photon, every solar wind particle, every burst of radiation for an entire year, and focus it entirely on a single spacecraft, and it would still not be enough to push that spacecraft to light speed. The universe does not run out of reasons to say no. It simply keeps saying it, with increasing force, forever. This means interstellar travel will always be slow. Even in the most optimistic scenarios with technologies that do not yet exist, with engineering achievements we can barely imagine, crossing the gap between stars will take decades at minimum. The universe is simply too large, and the speed limit is simply too firm. So we cannot go fast enough. That much is established. But let us press further. Let us assume, because I want to give every scenario its fair hearing, that somehow, impossibly, we built a ship that could travel at 20 or 30% of the speed of light. What would the journey itself be like? What would it do to the people aboard? The moment you leave the protective embrace of Earth's magnetic field, you enter what I can only describe as a shooting gallery. Cosmic rays, high-energy particles flung across the galaxy by supernovae, and other violent events bombard everything in interstellar space with continuous, remorseless force. On Earth, our atmosphere and magnetic field absorb or deflect over 99% of this radiation. In deep space, there is nothing between you and those particles. Nothing at all. Astronauts aboard the International Space Station, which sits only 400 kilometers above the surface and still benefits from partial magnetic shielding, receive approximately 150 millisieverts of radiation per year. That is already 50 times the average annual dose for someone living on the ground. In true interstellar space, unshielded, the exposure would be dramatically and dangerously higher. You might think the answer is shielding. Thick walls, dense materials between the crew and the radiation. And it is true that shielding helps against some types of radiation. But high-energy cosmic rays have a troubling property. When they strike dense shielding materials, they produce what physicists call secondary radiation, a shower of additional particles created by the collision itself. You try to block the bullet, and the shield creates shrapnel. The harder you try to stop the radiation, the more complex and dangerous the problem becomes. Over a journey measured in decades, the cumulative radiation exposure for any crew would cause catastrophic biological damage. DNA strand breaks, dramatically elevated cancer rates, cognitive decline, immune system failure, cataracts. The physics does not care about your mission objectives. It applies its rules regardless. And then there is the quieter threat, the one that does not announce itself with drama, but accumulates slowly, day after day, in the bones and muscles and hearts of everyone aboard. Weightlessness sounds peaceful. It sounds like freedom. The images we see of astronauts floating serenely through spacecraft interiors have a certain dreamlike quality that makes weightlessness seem like a gift. It is anything but. Without gravity's constant pull on your body, your bones begin to lose density at a rate of between 1% and 2% per month. Your muscles, including, crucially, your heart, atrophy. They shrink. They weaken because they no longer need to work against gravity's demand. Astronauts aboard the International Space Station exercise for 2 hours every day using specialized resistance equipment, and they still lose bone mass. After 6 months in microgravity, some never fully recover their original bone density. Some never will. Now stretch that timeline to 40 years, to 80 years, to a multi-generational voyage spanning centuries. The human skeleton, by arrival, would be so fragile that simply stepping onto a planetary surface feeling gravity's grip for the first time in a lifetime could shatter it. The heart, diminished by decades of easy work, might not sustain a landing. The eyes, which change shape in microgravity due to fluid pressure shifts, might have suffered permanent damage. The body, which took millions of years of evolution to perfect for one specific environment, would be paying the full cost of being removed from that environment for long enough. Artificial gravity is theoretically possible. If you spin a spacecraft at the right rotation rate, the centrifugal force mimics gravity. But building a rotating habitat large enough to house a crew across decades of travel, structurally sound enough to survive interstellar conditions, and light enough to actually accelerate to the required speed, that is an engineering challenge of a completely different order from anything we have attempted. We have not come close to solving it. And this is the part that I think people overlook most readily, because it does not fit neatly into the language of physics or engineering, there is the psychological dimension. At the speed of light, a message from Proxima Centauri takes 4 years and 3 months to reach Earth. A question sent home, and its answer received, would take over 8 years. There are no video calls, no news updates, no connection of any kind to anything human outside the walls of the ship. For decades, the crew would be more isolated than any human being in history has ever been. More isolated than the most remote Antarctic expedition. More isolated than any prisoner. More isolated than any hermit or castaway. Irrevocably and completely cut off. Isolation studies conducted right here on Earth, where volunteers are sealed into simulated spacecraft environments for months at a time, consistently produce the same results. Depression, anxiety, cognitive impairment, interpersonal conflict that escalates in enclosed spaces over time. And those volunteers know, at every moment, that they can leave, that there is a door, that the world outside is still there, still going on, still connected to them. On a real interstellar mission, there is no door. There is no abort button. There is no rescue. There is a metal container hurtling through an emptiness so complete that the nearest help is measured in light years and decades. Some theorists have proposed the concept of generation ships, vast vessels carrying entire communities, designed not to complete the journey in one lifetime, but to sustain human life across multiple generations until some distant descendant arrives at the destination their ancestors chose. It is an idea that has a certain epic grandeur to it, and it raises questions so profound and so troubling that I do not think we have begun to honestly reckon with them. How do you maintain social stability across centuries in an enclosed environment? How do you preserve institutional knowledge, technical competence, and the memory of a mission across generations that never chose to be part of it? History, the full, unvarnished record of human social behavior across time, shows us that our societies fracture, evolve, and forget over timescales far shorter than the journey would require. Languages become unrecognizable within a few hundred years. Religions split and transform. Governments collapse. The idea that a sealed community, inheriting a mission from grandparents they never knew, surrounded by the same walls from birth to death, could maintain coherent purpose across a millennium, that idea contradicts almost everything we know about how human beings actually behave across time. And one final thing. One more physical reality that does not receive enough attention. Space is not empty. It looks empty. When you gaze at a photograph of deep space, those vast black regions between the glowing nebulae and the distant stars, it appears utterly void. But it is not. There are particles, dust, hydrogen atoms, microscopic grains of matter drifting through the interstellar medium. Under ordinary circumstances, these are irrelevant. A spacecraft moving at the speeds we currently travel encounters them gently, the way a ship encounters water molecules harmlessly, invisibly, but at 20% of the speed of light, a grain of sand carries the kinetic energy of a hand grenade. A pebble strikes with the force of a bomb. At those velocities, the spacecraft is traveling faster than its own sensors can scan ahead. It is literally outrunning its ability to see what is coming. And we are not talking about a brief dash through this environment. We are talking about decades of continuous exposure to whatever lies along the path. Micro impacts, dust clouds, stray particles. The probability of surviving all of that, unshielded, across a journey measured in human lifetimes, is not in our favor. So, let us take stock of where we are. The nearest star is 40 trillion kilometers away. Our fastest probe would take 6,000 years to reach it. The rocket equation makes conventional propulsion useless at these scales. Alternative engines, ion drives, nuclear thermal, nuclear pulse are promising, but exist only as concepts. And even at their theoretical best, they would take a human lifetime to complete the journey. The speed of light sets an absolute ceiling on velocity that cannot be negotiated with or engineered around. Radiation in interstellar space would devastate any crew. The human body deteriorates in microgravity in ways that become catastrophic across decades. The psychology of total isolation is a form of suffering that engineering cannot shield against. And at the speeds required, space itself becomes a lethal environment of micro-impacts and particle bombardment. Now, some people at this point will want to invoke wormholes, warp drives, the possibility of shortcuts through spacetime that bypass the speed limit entirely. And I want to address this honestly, because these ideas deserve neither dismissal nor uncritical celebration. They deserve the same honesty we have applied to everything else. Warp drives, as proposed by the physicist Miguel Alcubierre in 1994, are elegant. The mathematics is real. The concept involves contracting spacetime in front of a spacecraft and expanding it behind, creating a kind of wave that carries the vessel without the vessel itself technically exceeding light speed. The equations do not obviously forbid it, but the energy required to create such a distortion in spacetime has been calculated, and it is equivalent to converting the entire mass of Jupiter into pure energy, not fuel, mass. The entire planet Jupiter, annihilated completely, might provide enough energy for a single journey. And that is before addressing the question of exotic matter, a form of matter with negative energy density, required to stabilize the warp bubble which has never been observed in nature and may not be permitted by nature. Wormholes, similarly, exist as solutions to the equations of general relativity. Spacetime can, mathematically, fold. Two distant points can, in theory, be connected by a tunnel through higher dimensional space. If such a structure existed, traversing it might take only moments. But wormholes, if they form at all in the natural universe, collapse in timescales so brief that no physical object could pass through. To keep one open would require exotic matter again, and we have never detected exotic matter. We have never even convincingly confirmed that it can exist. These are not technologies on the horizon. They are not engineering challenges awaiting funding. They are mathematical possibilities, beautiful, internally consistent, deeply interesting, as theoretical structures that may have no physical counterpart in the actual universe we inhabit. There is a profound difference between what the equations permit as a solution on paper and what matter and energy and spacetime actually do in reality. We have sometimes confused the map for the territory. In this particular case, the territory appears to have closed the road. And so, what does all of this mean? What are we left with after following this thread to its honest end? I think we are left with something that looks, at first, like grief. And I think that is appropriate. There is something genuinely sorrowful about understanding that the universe has placed the stars just out of reach, that the longing our species feels the ancient, wordless pull toward other suns will not, in all probability, be answered by our bodies arriving anywhere. That the great dream of interstellar exploration, the one that has animated science fiction and scientific imagination for over a century, runs directly into laws that do not yield. But I want to suggest to you that grief, when it is honest, when we allow ourselves to feel it fully rather than rushing past it into false comfort, has a way of clarifying what actually matters. And what becomes clear, once we sit with the reality of our situation, is something surprising. We can look, we can listen, we can understand. The James Webb Space Telescope, at this very moment, is doing something that would have seemed miraculous to any previous generation of human beings. It is capturing light that has passed through the atmospheres of planets orbiting distant stars. It is analyzing that light with extraordinary precision, searching for the chemical signatures of life. Carbon dioxide, methane, oxygen, in combinations that only biology is known to produce. We cannot go to these worlds. We cannot walk on them, or breathe their air, or touch their soil. But we can read them, we can know them, in a real and meaningful sense, from across an impossible distance. That is not nothing. In fact, I would argue it is extraordinary. To be able to stand on a small, warm, improbable world in a corner of an ordinary galaxy, and to read the atmospheric chemistry of a planet orbiting a star 4 light-years away. That is an act of understanding so remarkable that I do not think we have yet found the language to properly honor it. We are a species whose intellect reaches further than our rockets ever will. And I want to sit with that for a moment, because I think it is one of the most important truths about what we are. In all the history of life on this planet, in 4 billion years of evolution, in every organism that has ever lived and breathed and moved and reproduced, we appear to be the first to have developed the capacity to understand the universe at a scale vastly beyond our ability to physically explore it. Every other creature navigates the world through immediate experience, through what can be touched, tasted, smelled, heard, seen with the naked eye. We have built instruments that extend our senses across billions of light years. We have developed mathematical frameworks that describe the geometry of spacetime, the quantum behavior of subatomic particles, the life cycles of stars. We understand things that we will never, in any physical sense, reach. And that capacity to know something fully without being able to touch it may be the most remarkable thing about us. So I want to offer you 4 things to take from today, not as a list of tasks, not as homework, as genuinely useful ways to carry this truth in a way that serves you. The first is this: learn to distinguish between problems and laws. In your own life, in your work, your relationships, your ambitions, there is an important difference between a situation that invites creative effort and a constraint that is structural and fixed. Not every wall is meant to be climbed. Some walls define the room we actually live in, and learning to direct your energy toward what is genuinely changeable while accepting with grace, and even curiosity, what is not, is one of the most energy-conserving and psychologically freeing habits a mind can develop. When you feel yourself pushing against something that will not move, pause, ask yourself honestly, is this a problem or is this a law? The answer changes everything about what to do next. The second, let the scale of the cosmos recalibrate your perspective. Not as a trick to diminish your concerns are real, and they matter, and the scale of the universe does not make human pain trivial, but as an honest framing device. Return sometimes to the marble in your hand, the 30-meter sun, the 8,000-kilometer star, and then return to your life and its difficulties. Something in the proportions shifts when you do this sincerely, not toward indifference, toward a kind of spaciousness, a sense that this moment, this one specific, ordinary, unrepeatable moment of being alive on a warm, breathing planet is rarer and more astonishing than we usually remember to notice. The third. When you cannot reach something, ask what you can understand about it from where you stand. This is what our telescopes teach us. This is what the Webb telescope demonstrates every day. The inability to physically arrive somewhere does not preclude the ability to know it deeply. In your own life, there will be places and people and possibilities that remain inaccessible to you for any number of reasons. The instinct is to treat inaccessibility as total loss, but understanding honest, careful, patient understanding is its own form of intimacy. It is not the same as arriving, but it is not nothing either. And the fourth, make peace with the beautiful impossible. This is the hardest one, and perhaps the most important. There are things in physics, in life that will not yield to effort or ingenuity or time. The mature response to permanent impossibility is not despair and not denial. It is something rarer and more difficult. The capacity to find the thing beautiful anyway, to stand at the edge of what cannot be crossed and feel wonder, rather than only grief, to say, with genuine sincerity, I see you, I understand you, I cannot reach you, and you are magnificent. This is not passive acceptance. It is the active, difficult, deeply human choice to let reality be what it is, and to find, within those constraints, the full texture of what it means to be alive and curious and conscious, in a universe that does not owe us easy answers. We began today at the edge of an impossible distance. We looked at the 40 trillion kilometers, the 6,000-year journey, the rocket equation that consumes worlds, the speed limit written into the bones of space-time. We looked at the biology that would fail us, the psychology that would fracture us, the physics that would bombard us. We looked at wormholes and warp drives and acknowledged, without flinching, that they remain mathematical dreams rather than physical realities. We followed the thread all the way to its honest end, and something changed. Not from hope to despair, from one kind of hope to another, from the hope that says we will get there eventually, given enough time and money and will, to the hope that says we can understand this fully and honestly, and that understanding itself is a form of arrival. That to know the size of something truly, viscerally, without looking away, is its own kind of journey completed. You are not diminished by a universe that is larger than your reach. You are defined by the fact that your mind can measure what your body cannot cross. No other creature on this planet, perhaps no other creature anywhere in the observable universe, has stood on a small, warm, improbable world and mapped the distance to its nearest neighbor with enough precision to know, with certainty, that it cannot be reached, and then written about it, and made art about it, and built telescopes to study it, and felt grief and wonder and love for something it will never touch. That is not a failure. That is the most extraordinary thing I know of. You were not built for every distance, but you were built to understand them all. If something in this conversation settled somewhere new for you, if a single moment landed differently than you expected, or shifted the way you are holding some impossible distance in your own life, I would genuinely love to know about it. Leave a thought in the comments. Not a quick reaction, a thought. Tell me which idea surprised you, or which one you are still sitting with. That kind of honest exchange is why I am here, and it matters more to me than I can easily say. And if you feel that this is a conversation worth continuing, one that takes science and uses it as a mirror for something more personal, more human, more alive than the facts alone can hold, then please do subscribe. Not out of obligation, only if you felt, somewhere in the last little while, that understanding the universe more honestly made you feel more, not less, at home in it. The stars will wait. They have been waiting for billions of years. And even if we never cross that canyon, even if the gap between us and Proxima Centauri remains uncrossed for as long as our species endures the fact that we stood at the edge and understood how wide it was and felt something in response to that understanding and chose to keep looking anyway, that matters. That is enough. That, I think, is everything.